the reports are simply not robust. They're not suitable for clinical implementation. Lots of these algorithms have FDA approval. Lots of these are being sold to the community. But if interrogated in an intellectual and robust manner, they're simply not yet up to scratch. And I suspect quite a lot of this is because there's a suspension of sort of cynicism, because you're like, well, it's AI, it's intelligent, whereas in fact it's not quite the case. And this extends into sort of the low bar that a lot of these papers seem to slide under, because they're talking about a sexy topic. And this was a review of articles that were looking at studies and finding only 6% of them performed external validation. And in those that did, there was an 80% drop. 80% of them had drops in performance, with a quarter of them having a very substantial drop. So if instead of thinking of this as AI, we think of it as statistics 2.0 or advanced statistical algorithms, we can then start to bring the field towards where we need it to be. So enough of my curmudgeony. I'm now going to moan that there's not enough AI, particularly in structural heart disease. So this was a search I did on PubMed 2 days ago while preparing these slides. And we can see a ratio of about 10:1 of papers in coronary artery disease versus structural heart disease. And understandable, coronary artery disease, #1 killer of the world. But if we look at valve disease, it's increasing in prevalence. And that's true across the entire globe, other than in the three blue countries there are Somalia, Iraq, and Syria. And we can see why they might have alternate reasons why their calcific aortic valve disease isn't increasing in prevalence, given that it's a predominantly elderly population. So we've got diseases that are increasing in prevalence, increasing mortality despite improving therapies. So really an area of need. The other is, as Ed is saying, where are we seeing the time savings? So it takes me about 5 minutes to say there's no coronary artery disease, 10 minutes if I want to be super sure there's no sneaky little pulmonary nodules hidden on the edge of the CT scan. Whereas it takes me 45 minutes to an hour to churn out all these numbers here. And churning out numbers is what machines do really well. And then this is therefore going to save huge amounts of clinical time. So we've got a clinical need and a potential clinical impact. So really shouting out for more AI in structural heart disease. Part of the slowness of uptake might simply be that statistics 1.0 in structural heart disease is actually quite good. So this is where we use shape-based analysis, deformation, to what we know the structures are. So just using a maths-based approach. And we've got papers dating back more than a decade now in this sphere where we generate quite nice annuli and quite nice coronary heights. The only problem being is, since it's trying to force these objects into a known shape, it can overlook critical things like what happens whenever you have bicuspid valves or severe LVOT that change that shape from what the machine is expecting to see. This was 2 clinical cases that we had that fortunately they were picked up at the last minute before the TAVI valve was put in, where the sizing had been just transferred from the auto contours into the report, but whenever you manually contoured them, corrected for the different angle of the annulus in bicuspid valves, you suddenly get much smaller annuli. And you can see how in the automated approach here is pulled in the LVOT calcium as part of the annulus. So this leads nicely into one of the interesting AI algorithms that are out there, which is characterizing the valve. Now, this is not because I need someone to tell me what a bicuspid valve is. It's not going to reduce my reporting time. But what it can do is, if it can pick up there is a bicuspid valve, it can then say the numbers you're now going to get from the algorithm are not accurate because they've only been trained in 10 bicuspid valves and 1,000 tricuspid valves. So you might want to go back and manually check these things yourself. And this showed that they could train this algorithm very nicely to pick out the root, the valve morphology and the calcification here, and bring all these pieces of information together to diagnose with quite nice accuracy the presence of a bicuspid valve. So going on to this annular segmentation that we've talked about and how much time it can potentially save, this is a nice study where they looked at a 2D convolutional neural network for the definition of annuli, and did so with a very high degree of accuracy. And if we look at the Bland-Altman plots, the left-hand one, is the machine versus reader 1, whereas the right-hand one is reader 1 versus reader 2. So we can see that there's equal agreement between the CNN and the reader as there is between people themselves, so nice and reproducible. The only limitation of this is it is just a 2D convolutional neural network on a predefined annular plane rather than picking up the annular plane itself. And just like its measurements were in equal agreement or disagreement with the humans as the humans were between them, the downstream sizings also saw equal shifts between the humans and the machine. And what's particularly nice if we compare statistics 2.0 with statistics 1.0, we can see a nice reduction in the limits of the agreement. So we are seeing improved quantification of the annuli with the new techniques. The same group then went, well, yes, we've looked at a 2D convolutional neural network. What about 3D? Can we start to pick up the hinge points and the coronary heights? And very nice proving with heat maps that they are picking up the structures they expect in the correct location for each of the coronary cusps and the coronaries. They then look at how this is going to measure the coronary height, and again we see a lovely reduction in those limits of agreement between coronary heights measured with the algorithm versus humans on the more advanced statistics 2.0 compared to the traditional techniques there. Now, of course, these weren't both performed in the same study, so they're not being directly compared to one another, but certainly if we're comparing the outputs of the relative metrics between the two studies, looking very favorable. But we are still learning how machines learn, and this goes back to my earliest slide, and I really like this because this is two different approaches to the identification of the annulus. One is a recursive neural network, and the other is cascaded neural networks, so two iterative approaches to the identification of the annuli. One thinking very much like a machine, it's just starting at the data, and it's a bit like CSI. It starts with the full data set, but to the low resolution, and then it goes enhance, and then zoom in, enhance, and it keeps doing that until it gets a nice high resolution of the annulus. Whereas the cascaded neural network is trying to teach the machine to think like a human. It's like, first off, let's identify